So in today's video I want to look at one of the applications of derivatives, and it's usually one of the first things you see in a calculus class, and that is projectile motion. So if we think about a projectile, that's some object that is thrown or dropped or shot through the air. It's going to go up and then come back down because gravity pulls it back down, and that's obvious to us. But through higher level math and physics, we found that projectiles can be modeled by a quadratic equation because the pull of gravity is equal to -32 feet per second. So from that we can derive a formula that the position of a projectile is equal to -16 t squared plus the initial velocity multiplied by t plus the initial height. And you'll probably see this formula in your textbook. You probably will see this in your calculus classes. And this is simply a quadratic equation that's modeling the motion of a projectile. So the first term, -16t squared, is representing the pull of gravity. The second term, the initial velocity v sub naught times t, is simply the initial velocity, whatever. If it was shot at 50 feet per second, it would be 50 times t, the variable, plus the initial height. If it was dropped from 100 feet, it would be plus 100. And we can use this to model the motion of any kind of projectile. But what's quite interesting, and where we begin to introduce derivatives, is that if we consider this quadratic equation, our x-axis in this case is time, and our y-axis is the position. Well, if we're talking about position in relation to time, if we want the rate of change of that, because the derivative is a rate of change, the rate of change of a position with respect to time is its velocity. So we can say that the derivative of the position function, s prime of t, is equal to a velocity function. So we can find the instantaneous velocity of this projectile at any time using a derivative. And furthermore, if we think about what the derivative of the velocity function is, a derivative is a rate of change. And what is the rate of change of a velocity with respect to time? The rate of change of velocity, v prime of t, is acceleration, a of t. So we can use our derivatives to find the instantaneous velocity and acceleration of these projectiles. And I should take a moment here to note that this is when we're not dealing with any air resistance. In most real-life problems, you are going to have some type of air resistance and other forces, and it requires higher-level math and physics techniques to be able to compensate for it. But this is an introduction to what we can do with derivatives, and it will help prepare you for more advanced things you'll see later in calculus and in physics as we get into real-world problems. But the idea behind this is simply that because the pull of gravity is -32 feet per second, we're able to derive this quadratic equation that represents the position of the projectile, and from that we can do a lot with it. Because if we think about what this means in relation to a graph, where it intersects the y-axis is the height it was initially projected from. So if you're dropping something off the top of a building or shooting something from a higher level, the top of something, you're going to have the curve intersecting the y-axis above the x-axis where it has positive height. And as a result, you'll notice that you have a 0 where it intersects the x-axis on the negative side and a positive. And this is simply a result of the -0 is where it would have been coming from following that path if you reverted back in time. If you had negative time from the height it was shot from traveling that same path back down to the ground. The positive 0 is going to be where the projectile comes back down and hits the ground again. And an important thing that we can take from this is the maximum height, the top of this peak, where it continues up and then gravity eventually overtakes its velocity, and for a split moment it's completely stationary in the sky before it begins to fall again. We can find that extrema, the top point on the curve, using a derivative. Because if we think about it, that top point where it has gone up, it's reached its top point and just before it starts to fall, for the split second, the velocity is 0. So we can take the derivative of the position function, which we know is velocity, and just set that equal to 0 and solve for the time at which it's reached that height. And we can likewise find the time that it's spent in the air, because we can simply solve the quadratic equation and find the 0, which is the point where it hits the ground after coming down. So we can use this idea of projectiles and derivatives to find instantaneous velocity, acceleration, and other things. So I want to look at a couple things briefly in this video. Say we are given an equation to represent a projectile. S of t is equal to negative 16 t squared, which is gravity, plus an initial velocity of 16t. So it's initially being shot up or thrown or whatnot at 16 feet per second, plus an initial height of 32. So it was 32 feet up in above ground level when it was initially shot or thrown or whatnot. And I want to know, when does that reach its maximum height? Well, that maximum height is going to be when the derivative of the position function is 0, because we know the derivative of position is velocity, and that's going to simply be the derivative of this equation. We can just use our power rule along with sum and difference. We know that's negative 32t plus 16. So when does that equal 0? Well, that's a simple linear equation to solve. We move the 16 over and we get negative 32 is equal to, or 32t is equal to negative 16. Divide by negative 32 and we get t is equal to 1/2. So after 1/2 of a second, it's reached its maximum height. And then we may ask, well, how high was that maximum height? We can plug that time into the position function and find how high it was, because s of 1/2 is the height at the top of its arch before it begins to fall back. That's simply negative 16 times 1/2 squared plus 16, or 1/2 times 16, plus 32. And this is simply plugging 1/2 into the position function. We'll simplify and get negative 16 times 1/4 plus 8 plus 32, which when we simplify that will be 40 minus 4, which is 36. So 36 feet was the maximum height it reached. And another interesting thing we can do with it is find the velocity when it hit the ground, which is quite important. And a lot of times when we have a projectile, we want to know how fast is it traveling when it hits the ground, because that dictates the amount of force it creates when it hits the ground. So when is that projectile going to hit the ground? We said earlier that's the 0 of the quadratic. That's where it hits the x-axis. So if we throw our original position function into the quadratic formula, we can find that 0 and then plug that time into our velocity function to find what the velocity was then. So let's take our original position function, which we have up here, and find the zeros of it. So we know that will be negative 16 plus or minus the square root of 16 squared minus 4 times negative 16 times 32, all divided by 2 times negative 16. And that's simply using our quadratic formula from algebra. When we simplify that, we get negative 16 plus or minus the square root of 2304 over negative 32, which we can simplify because we can take the square root and get negative 16 plus or minus 48 over negative 32, which that gives us two solutions here. The solutions will be t equals negative 1 or 2. So we have to ask, why do we have a negative solution for time? Because we had an initial height. The negative is as if we started at the ground following the same pattern. The 2 is how long it took it to reach the ground. It was 2 seconds after it was initially shot or thrown up that it went up, then it fell back down, and after 2 seconds from the initial time it hits the ground, or it's hitting the x-axis on the graph. So if we want to know what is the velocity when it hits the ground, that's the derivative of the position function evaluated at 2. which is the same as the velocity function evaluated at 2. And we said that the velocity function was negative 32t plus 16. So that will be negative 32 times 2 plus 16, which when we simplify that, that's simply negative 64 plus 16, negative 48. And we're dealing with velocity, so feet per second. And that kind of makes sense if you think about it. We have a negative answer. Why is it negative? Because the object is falling. Because velocity has two components, a magnitude and a direction. That negative is telling us it's falling, and the 48 feet per second is telling us how fast it's falling. So that's a way that we can gauge how fast something's falling when it hits the ground instantaneously. That will tell us how much force it creates when it hits. So it's quite useful. And one more thing I want to touch on in this video is the idea of the acceleration function. Because as I said earlier, the acceleration is the derivative of velocity. Where we said our velocity function was negative 32t plus 16. Well, what is the derivative of that? V prime of t, which we said was acceleration, a of t, would simply be negative 32. Why is it negative 32? Because we know from scientific research and evidence the pull of gravity is negative 32 feet per second. So with any quadratic equation like this, when we have the pull of gravity as negative 32, our acceleration function will be negative 32. But there may be other instances when we have other factors that would give us an actual function where the acceleration may vary. So that's things you'll dive more into as you go deeper into calculus. But this is a basic introduction to projectile motion and understanding how we can use derivatives to find a lot of different things in these problems.